So this last fifth of the course, we made it to the last fifth of the course. Yay, the last little mountaintop. This is on energy, sources, sinks, and conversions. And so we're not just going to talk about the energy in small systems like our laboratory-based experiments, but we're going to expand it to show that the very skills that you learned even in freshman chemistry and honed again here in PChem too, can be applied to any scale, even at global consumption of energy. So we're going to be looking at the amount of energy consumed worldwide and compare that to the amount of enthalpy we get or the heat of reaction from oil and natural gas and so on. So I think it's an interesting application of the skills that you've learned as a chemistry major. And so we know that the first law, energy can't be created or destroyed. And so the total energy of the universe is constant, but it can be converted from one form to another. And we're going to be doing those conversions today for sure. If we're going to be going up to the global scale, we're going to need some more prefixes. Like we deal with kilograms or kilojoules and megajoules maybe, but now we're getting up to exajoules. So that's 10 to the 18. We rarely deal with exa, right? We get to, terabyte hard drives. I just got some new hard drives for backing up my videos. And so that's a terabyte, which is 3 orders of magnitude higher than giga. But then you can get up to peta and then exa. So that peta is 10 to the 15, exa is 10 to the 18. And we'll learn another thing too called a quad or a quadrillion BTU, British thermal units here. So a quadrillion BTUs is 10 to the 15 BTUs, and that is roughly an exajoule. It's 1.05, so it's off by 5%. So it's the same kind of thing. It's not exactly the same, but it's the same irritating difference that we have with like bar and atmospheres, right? So you'll see even our own government was doing so well. They were reporting all our numbers in exajoules, and then all of a sudden they switched to quads. And I'm like, why would you do that? We were a metric system, and it's one of the few times we were a metric system and like changed away from it. So another part of this course that we're going to cover here at the end is the conversion efficiencies. And so this is the overall series of conversion efficiencies, and this is a really good chart to have because this shows how we convert from chemical fuel to thermal fuel most of the time by making steam. Like if we're going to make electricity, we burn something, make heat, and capture that heat in steam. And so then that steam is thermal energy, and then we can spin a turbine. So we can take that steam, run it through a turbine, and make mechanical energy. And then that mechanical energy through a generator can generate electricity. So that's the path that we use to convert from a fuel, a chemical fuel, to electricity. But look at the hit that we take. 88% efficient. We lose, 12% of the heat that we make out the stack. We don't, the gas doesn't come out at room temperature, right? So there's some heat that's lost, but we did pretty good. We get 88% of those joules from burning natural gas or burning coal or what have you. But here's where we really get hurt. Spinning that turbine, we have to spin the turbine and the gas doesn't leave with no velocity and a cold temperature. It's still pretty hot when it leaves. And so these steam or gas turbines max out at this point with current technology around 46%. So we lose over half of those joules going just from thermal to mechanical. Now the electrical generation, that is really efficient. So we don't have a problem with the electric generators. It's this thing. Anytime we spin a turbine, then we lose a lot of our efficiency. So this is the overall energy flow. Now this is an old document. This is 2002, but we'll update it. But you'll see also how little it changes over the years. So here we have all of the different inputs. And this is put out by the U.S. Energy Administration, or Energy Information Administration. So yeah, you have, this electrical imports, that's just like cross-border electricity if we get it from Canada or from Mexico, very little. We have nuclear here, and then we have the renewables, hydro and biomass and other. So pretty small numbers. The big numbers naturally are natural gas, coal, and oil. So these are our fossil fuels. and we're in the 20s, 24 and 26 exajoules. And notice the net primary use. So this is the consumption of energy is 115 exajoules per year for the US. That's a lot of energy. Okay. And you can look at the efficiencies too. Look at all the different sources we have for electrical generation. I mean, we got a little bit that uses oil, but not much. Coal is the big heavy lifter. Okay, we use a lot of coal for our electricity. We use some natural gas, 1.8, a little bit of biomass, a little bit of hydro, and nuclear. And that all goes into this sector called electrical power, is converted to thermal energy, converted to mechanical energy with the turbine, run through a generator, and generates this much electricity that's distributed to the customer, 12.5 exajoules. And then this is the total that went in, 40.3. So we can calculate the efficiency of our electrical delivery. It's 31%. So we get 12.5 to our homes and our businesses and everything like that, but we consume 40.3 exajoules. So every sector has its own efficiency. Some of that electricity goes into residential, 8.9, 3.6 goes into industrial, a little bit goes into transportation. So all our electric vehicles, that's starting to grow, okay, naturally. This is 2002, so that's not a significant issue at that point. In 2002, these are golf carts, probably. I don't know for sure. We didn't have Teslas in 2002. But look at the residential. So this is, again, consuming 20.7, some directly, like natural gas, some indirectly, like electricity. So it's bringing in 20 exajoules and useful energy. Now, I don't exactly know what the Energy Information Agency is using to determine what is a useful energy in a home. But still, they calculate it 15% useful over 20% consumed. So our homes are running at about 75% efficient. Now that's on top of the electrical grid, so it's not perfect, but what comes into our home is pretty good. Industry, same thing, running at 80%. Why is industry better than home? Because industry has got a profit motive, a little bit stronger than our home profit motive, and that is that if they can save a few more dollars by using waste heat, so like they might have an industrial process that produces a product, and then they have waste heat. Well, they'll use that waste heat to heat the water for the building. They'll use the waste heat to heat the air for the building. So they'll grab some of those wasted joules and use them, and that's where they get up to from 75% for residential up to 80% for industrial. Now, think of the disruption. This seems like a huge amount of energy, and it is. Think of the disruption from COVID. Remember how little we traveled, how the supply chain dropped. Basically, our whole economy dipped quite a bit. Would you, I mean, like put a percentage on it? What do you think? I mean, you can measure our economy by how much energy we use. And so if our economy drops a dramatic amount, our energy usage should drop a dramatic amount. What do you think percentage-wise COVID did to our economy, like our energy usage? It's definitely dropped. During COVID, or like it was also like 2020, because it was really like spring of 2020 when it hit. So that year for 2020, starting in March when everything really shut down, 30%. What would you say? Higher or lower than 30? So like 20%. Yeah. What do you think? Okay, so between 30 and 50, say 40. What do you think? Okay. 2020, it only dropped maybe 8%, 9%. So when we talk about trying to reduce our energy usage and so on to a significant amount, think of what we had to do for COVID. And that was only, say, 10%. Let's say maybe 12 at max. And we would have to like reduce all the things we do, our standard of living, a dramatic amount, like 5, 10, 15 times what we did for COVID. Yeah. to have a substantial change of our energy consumption. So these are enormous numbers, and it's like we're on a freight train that weighs 1,000,000 pounds, and we're trying to save money by um, you know making sure after we peel an apple, we throw the apple peel off the train so that it reduces the weight. An apple peel off the side of the train is not reducing the weight of the train. I mean, the world consumption of energy is running big things, and we're just sitting on top of that. We are not really contributing our daily lives and our economies, very little contribution to this freight train of energy usage, running all of our factories, running all of our everything. So it's pretty dramatic. So here, our electrical efficiency actually went up a little bit, 34.8%. Here we have the residential numbers and everything, and transportation numbers. Here they changed the diagram a little bit. I don't like this. This is 2022. It came back up. So it dipped to one. You might say, well, that's 92 quads, and that's roughly 93 exajoules, okay? And the earlier number, 115, was from 2002. So you're like, well, that's a big gap. 2002 versus 2020, that's 18 years. But then what did it do in 2022? It went right back up to 106. Okay, so yeah, it didn't change much. 106 in 2022 versus 93 in 2020. So we could figure out, just using this diagram, again, also the electricity, only 8 exajoules of that is going into this electrical generation. When we're talking about electricity, we're talking about fossil fuels. Here's 12 and here's 8 here. So that's 20 out of that 35 is fossil fuels. Did I do the math right? Yeah. So 2/3 of our electrical generation is from fossil fuels. So when we'll see later, if we're going to convert that here, 21 out of 24 of our transportation is fossil fuels. Okay, and when we go through electricity, we'll see that taking into account the efficiencies, we're tripling our fossil fuel usage by using electricity for heating things and for driving our vehicles. So it's totally crazy if you're worried about CO2. So anyway, let's talk about this idea of lost energy. So this all of the useful energy that we use here, that comes out to be 37. And then all the lost energy, 59. What does it mean by lost energy? We know that energy is neither created nor destroyed. It's just energy we can't use, right? It's the smoke going out of the stack, the hot steam and everything. We've lost that energy. It's lost to us in terms of our usefulness, but it's not, quote, lost. It didn't go away. We just need to radiate it out to space. And so after we use this energy will also be radiated out to space. Okay. And so this was our USA. The rest of the world is about 3 times what we do. So we're at about 1/4 of the consumption of the whole world. And I have a whole list of things that we do with that. Like we produce more grains and more automobiles. We produce more PhDs and more patents and all of that stuff. So we do a lot in this country for the globe. Our economy is so huge that that's what we're producing with that 1/4. So this is all of the energy. So 425 exajoules is used worldwide, and that's consumed, used, and then emitted out to space. But then sunshine beats us by a long shot. Okay, so the sun is blasting the earth with 5,500,000 exajoules per year. Now that's the whole surface of the earth, but still, all the oceans and everything. But in terms of energy, we're not creating a problem with the temperature of the globe by the energy we're using. So all of the things we burn, all of the cars we drive, all of that stuff, they're focused on CO2. We'll get to that. But in terms of the amount of heat we generate, it's not warming the planet because of the heat we generate. we're at 425, and the sun every year is blasting us with 5.5 million. Okay, so we're sort of taking that off the table. It's not because we're doing things and burning things that we're generating heat. Okay, on our scale, all humankind would be 1/10 of a pixel on this scale. Just to put it in perspective, that's how much energy the sun is hitting us with. Okay, so all of these classifications, we have nuclear, we have renewables, and we have fossil fuels, which is natural gas and coal and petroleum. Let's look at our our chemistry skills and see if we can come up with these conversion factors. Okay, so we know what makes a good fuel. Up here, look at our QSAR, QSPR that we did in the lab. So carbon is the A coefficient, right? And hydrogen is the B. And so for every carbon atom, we get 427 kilojoules per mole. And for every hydrogen, we only get 88.2. So carbon is gold. What are we doing? We're taking that carbon and we're putting two oxygens on it. We're making two double bonds. Think of those double bonds. Those are really low in energy. So we're getting a huge amount of heat from the carbon. And the hydrogen, yeah, we're putting two hydrogens. So we're getting kind of half of an oxygen for every hydrogen. Okay, so we're not getting a lot per hydrogen, but we're getting a lot per CO2, per carbon. These were the specific heats. You know, this is the kilojoules per gram if we were buying this by mass. And you see it all kind of tapers off here to around 40 or 41 kilojoules per gram. These other ones down here, these oxygenates or maybe even nitros, you hear about people putting nitro in their automobiles. It's not really the nitro that is giving you the extra energy, it's the oxygen it's providing. So when it decomposes, then it's a less energetic penalty for producing the oxygen. So you can stuff more oxygen into the cylinder. So when they do and it's also nitrous oxide, it's not nitro, not nitrated organics. Okay, so let's look at natural gas. The economy runs on billion cubic meters, not grams of a substance. And so let's convert that over to number of moles. So a billion cubic meters, this should be simple for you guys to do. 10 to the 9 meters cubed. There's 1,000 liters per meter cubed, and we could use the ideal gas constant to get to moles. Okay, so we've got liters canceling here. Let's see what it is at 1 atmosphere. Okay, and then we've got 298 Kelvin because we're at SATP, standard ambient temperature and pressure. Okay, so the kelvins are gone. And so we end up with 4 times 10 to the 10 moles for a billion cubic meters. So that's a lot. How much energy is in a billion cubic meters? So let's just use our combustion enthalpy of methane. So you guys can do this. Y'all did this for the combustion experiment. Products minus reactants, right? We've got 2 waters. We can look up in the enthalpy tables what the enthalpy of formation is for for water, and for CO2, we've got 1 CO2. And then we're taking apart a methane, and we're taking apart oxygens, which is 0 because it's an element in its standard state. So this is straight from our class. Also, I think it was Chem 2. Delta H of reaction, negative 802 kilojoules for this reaction, or per mole of methane. So let's convert this over to billion cubic meters. Okay, so that's per mole of methane. We know there's 4 times 10 to the 10 moles per billion cubic meters. And so we end up with negative 32.82 times 10 to the 15 joules per billion cubic meters. This is peta. Not the organization, but the prefix. Okay. And so we end up with 32.8 petajoules per billion cubic meters. Now this is using our straight up in lab chemistry major skills. And sure enough, that's exactly what we see on the global sites. The World Energy Council is an interesting organization. They go around and ask countries to survey their natural resources. So we know kind of on a global scale what kind of amounts of natural gas are in Argentina or the United States or Mexico or Canada or whatever. And then they convert that over to the amount of energy that's in each country. And so they use 36 petajoules per billion cubic meters. So they're coming in a little higher. We're assuming natural gas is pure methane, but it's not. It has some ethane in it, which is a little bit more carbon, and it has some propane, which is a little bit more carbon. So it makes sense that natural gas would be a little bit higher. So that's where that number comes from. But still, it's pretty interesting and encouraging that using our regular old delta H reaction that we got this close to the accurate conversion for natural gas. Let's do oil or hydrogen. Hydrogen too. We hear about the hydrogen economy. So this is the enthalpy of combustion for hydrogen. And it's 9 petajoules per billion cubic meters. And so it's 113 gigajoules per ton of hydrogen compared to 50 gigajoules per ton of methane. So it is much higher if you had a ton of hydrogen. The problem is we can't just poke a hole in the ground and have hydrogen come out. There's really no natural hydrogen on Earth because we have an oxidizing atmosphere. So all the hydrogen that was in the planet back in the day, if there was any, has already been oxidized to make water. That's where all our water came from, so reacting with oxygen. Okay. So we're really just not going to get any energy from hydrogen. Let's look at petroleum and coal. So here's oil. Oil is a long chain hydrocarbon, we can assume. Let's just pick 18. I just kind of grabbed that number. I knew it was long. And so 1 ton of oil, so here's a number you may not know. So a ton of oil is 1,000 kilograms. So that's a metric ton, 1,000 kilograms, or 10 to the 6 grams. And so that's going to be this many moles of this oil. Okay. Delta H of combustion for that, we can do that reaction. You got 18 CO2s and 19 waters, and you subtract the mole of oil for its enthalpy of combustion, and we get 43 times 10 to the 9 joules per ton of oil equivalent. Now this TOE, let me see, I'm going to write that out somewhere. They're saying it's equivalent to a ton of oil. So that's, if a ton of oil gives you a certain energy value and you calculate some other energy value, you could use this conversion to say, well, how many tons of oil would that be? That's equivalent to a ton of oil. So that's what we mean by ton of oil equivalent. And so this is 43 gigajoules per ton of oil equivalent. And the World Energy estimates the energy content to be 42. So we're a little high. And that makes sense because, again, if you're digging crude oil out of the ground, you've got some oxygenates, you've had some oil that's reacted with oxygen, you've got some sulfur compounds and things like that. Those things do not produce as much energy. So this is for natural oil, the 42 gigajoules, that's the World Energy estimate. And then coal, what would you assume coal to be? Carbon, right? And so what coal is, if you want it, you could make your own coal, charcoal. You can take wood, put it in a hot environment, and what is wood? It's cellulose. And cellulose is, what's the term for it? Sugar. Also sugar, cellulose, and starch is what? Carbohydrates, which is CH2O. So if you heat it up, the H2O leaves and leaves behind the C. So that's what coal is, or charcoal is. It's heated up carbohydrates, and you heat it up enough, it thermally decomposes and the water leaves and leaves behind the carbon. Okay, it's a very energy dense substance. So if we just assume it's all carbon, delta H of combustion is negative 393.5. And if we're dealing with a ton of that, then we have that many moles of carbon. And so this would give us a ton of coal equivalent. So that's 32.7 tons of coal equivalent. TCE is coal. And the World Energy Council estimates it to be 29. Now we're thinking of pure carbon coal. What do you think we dig out of the ground? It's not pure. It's got some calcium carbonates and things like that that are in it. And so you'll have various coal sources that are more or less pure, but so that's why it comes in at a little bit less at 29 for the things that don't burn as well. They're still the part of the mass, the ton, but they don't give as much energy. So, you know, it would be perfect, but still perfectly pure carbon coal would be maxed out at 32.76 kilojoules, or gigajoules, sorry. So this is a summary of, we did pretty well with our regular delta H of combustion estimates, but for the homework numbers, use these. I use the World Energy Council numbers for the homeworks. And so on some of the homeworks, you guys are calculating how many tons of coal it would take to run a household or whatever. And so use the World Energy Council numbers if you could. Okay. So now let's see, this is how much it takes to produce the energy we need. How much is in the world? So let's look at the world reserves. So these are the world combustible fuel reserves. So if we wanted to run the whole world on coal, 425 exajoules, that's a billion gigajoules, then we would need 4.5 billion tons of coal. Okay. And we have 14.5 billion tons of coal, and we have 847 billion tons of coal. So we've got more than we need. Not, I mean, it's only I'd say 1.5 orders of magnitude higher, but still. Natural gas, we have 209,000 billion cubic meters. And then this is the oil that we have. We have 409 gigatons of shale oil that we've identified, 223 gigatons of crude oil, 42 gigatons of bitumen. And so the cleanest fuels are the natural gas and the crude, that like the West Texas intermediate sweet crude. It comes out of the ground. It looks like cooking oil. So normally you think of crude oil as black and dirty and whatever. This sweet crude oil from West Texas is beautiful. Okay. So what are we looking at? We need about 14.5 gigatons of coal. We've got way more than that of coal. We've got a whole lot of oil. We've got a whole lot of natural gas. Okay. We have zero hydrogen. So even though they talk about a hydrogen economy, we don't have any hydrogen reserves. Hydrogen is a storage medium. Okay. Now, in terms of converting all of those to energy, if we take the natural gas, those billion cubic meters of natural gas here, and convert it to energy, that turns out to be about 6,000 exajoules. I updated these numbers in 2016. It's time to do it again, but notice from 2013 to 2016, we identified more natural gas, and we're now up to 9,000 exajoules of natural gas. We have petroleum. You convert all those petroleum numbers into exajoules using the conversions from the WEC, and we have 9,000 exajoules of petroleum. In 2016, it went up even more to 11,000. And then shale oil, 17,000. And coal, we had identified in 2013, 24,000 exajoules of coal. Now we're up to 37 as of 2016. And then nuclear, 9,000. So if you just add up all the black numbers, it's 65,000 non-renewable, 65,000 exajoules non-renewable. And we use 425 a year for the whole globe. Okay. And then renewables, hydroelectric was 90, wind, and these are exajoules per year. So these go as long as the devices are working, provide this much energy each year. Wind, 630, biomass and wood, 1,300. So total renewables are 2,020. Already, the capacity of our renewables is greater than 425. Okay. And remember, so this is sort of, in terms of addressing the question, are we going to run out of energy sources? The answer is no. Because if you're using 425 a year and you've got 65,000 in the bank, you're good for quite a few years. Okay. And so we have 153 years of non-renewables without technological improvements. As of 2016, we have 198 years of non-renewables. So it's getting better, not worse. okay, of non-renewables. And then if you throw in renewables, we have say 65,000 in the bank. We use 425 a year, and we've got a regular income possibility of 2,000 a year. So the conclusion is we don't have a energy source problem. We have way more energy sources than we consume. Okay. So here's how it's broken down in terms of what's possible with our fossil fuels and our renewables and then nuclear. We haven't even addressed nuclear. Which energy source was not shown on the previous 10 slides? Nuclear wasn't, and then there's another one. No, it was on there. It was in the other renewables, biomass and wood, solar. Yeah, so all fossil fuels added up to 84, and the sun hits us with 5.5 million. Okay, so now that's really our energy balance coming in. We have all of these non-renewables, and we have 5 million per year coming in. I put this in terms of dollars because you guys are starting to learn about your expenses and how much you spend a month. Okay, and this is the same thing with energy, you know. So if we could only harvest 15% of that energy, that would give us 825,000 exajoules. We can't cover the whole globe with solar cells, but 0.1% of the globe would yield 825 exajoules per year solar. Okay, so there really is no energy supply problem. We have more energy sources than we could consume. Even if we doubled our consumption, and it has not grown that much, even though technology has grown up, we've made things more efficient as we've gone along. So what about pollution? Well, we got to pay attention to that, right? So this, I think, is one of the most valuable things in the course, completely valuable. So if you're at all drowsy, wake up right this second and pay attention to this definition, because this definition will clarify your thinking in terms of how we interact with the environment. Okay? Have you ever thought about the definition of a pollutant or pollution? Right? If you were to define it, what would it contain? Well, the definition of a pollutant or pollution is a loss of control. It has three parts: loss of control of a concentrated substance that causes harm. So if it doesn't cause harm, it's not pollution. If it's not concentrated, it's no problem. And if you have control of it, it's not been released. So you can focus on those three things, and that is how we fight pollution. Harm is subjective, but you might say, okay, toxicology. You got arsenic in the drinking water. Okay, that's a problem. You haven't controlled it. If it's concentrated enough to cause harm, now it's a pollutant in the drinking water. If you were to precipitate that out with some sulfide or something like that, then you've gained control of it. It's a solid now, and you know where it is. It's not in the drinking water. Okay. So concentration is, again, subjective. It's the toxin is the dose? Is it a high enough concentration? Is it safe? I mean, you probably have arsenic in your drinking water, but it's at a low enough level that your body can manage it. It's when it gets too concentrated that's a problem. But control is not subjective, and this is the one we focus on. So that arsenic example, if we were to precipitate that arsenic out, filter it, set it aside, we have control of it, it's no longer pollution. It may still be a concentrated substance. It may cause harm if you ate it, but you've got control of it. You're not going to let people eat it. Okay, so this control idea is what we focus on. So solids are very easy to control. If you could precipitate something out, you could set it in a container, you could monitor it, you could know where it is. Liquids are less easy to control. You can put them in containers, but containers can leak, especially over long periods of time. And then gases are terrible. Gases, if you have a hole in the top of a liquid container, no big deal. If you got a hole in the top of a container with a gas in it, you're not controlling the gas. It escapes. So avoid gaseous pollutants at all costs if you can. Okay. Let's look at the air quality. It's an old chart, but the same trend has continued. You see the population has gone up here. You see the energy consumption has gone up slightly. You see that CO2 emissions have gone up. So these are all of those three numbers. Up there, you have the vehicle miles traveled, quite a bit more. Gross domestic product gone up, and tracking 6 aggregate emissions. So nitric oxides, sulfur oxides, and lead, and so on. These gaseous emissions have dropped. So we're getting better at controlling those emissions. So how we do this is we took the sulfur out of diesel fuel. That was a big source of sulfur oxides from driving all of our semi trucks and our regular diesel vehicles, our diesel trains and so on. So dropping the sulfur content in diesel has dropped the SOx or sulfur oxide contaminants. Sulfur oxides get out into the environment, they react with water, and they make sulfonic and sulfuric acids. And then they fall out of the sky and get on our crops, and it's acid rain that degrade our buildings and so on. So we want to get rid of the sulfur oxides. Catalytic converters work. So unburned hydrocarbons, when they leave the tailpipe, can react with light in the atmosphere and produce oxidizing smog. And so this photooxidizing smog is dangerous. It harms people's, with asthma and so on, people with breathing issues. And so we've dropped those concentrations of unburned hydrocarbons using catalytic converters. So that's a reactive surface in the exhaust stream of a vehicle that these unburned hydrocarbons will land on, and oxygen will land on. And what it does is it is a catalyst, so it catalyzes the breaking of that oxygen double bond and catalyzes the oxidation of those hydrocarbons. And so essentially burning the unburned hydrocarbons on the surface of the catalytic converter. And so mostly CO2 comes out instead of unburned hydrocarbons. And then stack scrubbing. So in our coal-fired power plants, the somewhat pollutions and somewhat reactive gases come out, and they are sprayed with water. So they spray the water in all of those like lead oxide and mercury oxide and all of those contaminants get entrained in that water and fall out to the bottom, calcium oxides too. And then so steam comes out the top. So we're dropping out all of the water soluble oxides, and we have the ash from that burning that collects in this pool. Then we concentrate it and we mix it in with concrete. Once again, it's no longer pollution if we have control of it. So we sequester those oxides and we put them in our concrete. And so we're standing on it. We're probably standing on some fly ash from coal-fired power plants that was mixed into the concrete to make this building. It's not going anywhere. We have control of it, so it's not pollution. So anyway, that's pretty impressive what we've done in terms of reducing pollution. Now, we've done this in the U.S. in really well, okay? Other countries, not so well. Okay, so you can go to other countries, they have the same sort of push for a modern society as we do, but you can see the air quality is terrible, mainly because they don't scrub their stacks. Let's talk about home energy use. So Entergy Texas, that's our electrical generator here, they define a typical customer as a 1,000 kilowatt hour per month user. So what in the world's a kilowatt hour? Okay, and how many gigajoules per that is a year? Is that per year? So here's 12,000, so 1 year, 12 months, 12,000 kilowatt hours per year. All right, so a kilowatt, you know what a watt is? A watt is a joule per second. So that's 1,000 joules per second. So we can get rid of the kilowatt part. And then we have a per second here. And how many seconds are in an hour? Well, 3,600 seconds per hour. So we can get rid of the hour and the seconds. And so now we've got joules. So we've got 12,000 thousand. Okay. And then another 3.6 thousand. So we have 3,000s. That's where the giga comes from. That's 10 to the 9th. So we end up with 43 gigajoules per year that we use in a typical home of electricity. So how much coal, oil, or natural gas could you run your typical home on? Now that we have a gigajoule value, we can figure out how many tons of coal we have. So using those World Energy Council numbers, we get 1.47 tons of coal would run our house. Fair bit. Okay, what about oil? A little bit less, 1.03 tons of oil. And then 0.0012 million cubic meters of natural gas. Okay, and even smaller amount, or more hydrogen actually. Now, this does not take into account, we're talking about energy usage, electricity. So let's take into account let's take into account the efficiency. So look at this, 1.5 roughly, 1.5 tons of coal. If we take into account that our electrical grid is only 31% efficient. Now look at the scale I want to teach you here. Everything is joules, but let's put subscripts on our joules. So we want joules of electricity, 43 gigajoules of electricity per year, and this is the amount of electricity we get from our heat source. It's 31% efficient. That was from that electrical, Energy Information Agency number. Okay, and so then when we convert that to coal, it's 4.7. So I asked you the question, does this inform your opinion of using electricity to heat things? If you go in your house, in my house, we've got an electric water heater, we've got an electric stove, and electric heating for the house, okay? And yet we could have had like a natural gas heater, a natural gas stove, a natural gas water heater. By going with electricity and generating the electricity with a fossil fuel, we've more than tripled the amount of fossil fuel we've used. Isn't that crazy? And yet down here in New York and in Washington, they want to ban natural gas heaters and stoves, which would more than triple the fossil fuel use. Now that would be a great idea if we were running 100% on nuclear, okay? Because nuclear doesn't use any fossil fuels and doesn't put out any CO2. But when they think they're being like green by going to electrical cars and electrical appliances, we're actually tripling the amount of CO2 we put in the environment because we're not on nuclear. Nuclear is the only one, and wind and solar. Those are the only ones that don't put out any CO2. All of the ones that use combustion put out CO2. So how much CO2 does a typical home produce? Well, using the numbers here that you see, we could take that tons of coal equivalent, convert it to carbon and convert it to CO2. That's 17 tons of CO2. If we were using oil, it'd be 10 tons of CO2. If we're using natural gas, it'd be 6.8. Notice natural gas is the smallest amount. And so when we determined that we could get more gas out of shale deposits by cracking them open with hydraulic fracking, our natural gas usage went up, which meant our coal usage went down. So the United States dropped its CO2 emissions by a dramatic amount, even without like changing our technology or our lifestyle, by switching more over to natural gas, because natural gas produces less. In fact, this is less than half for the same amount of electricity. So is this a lot? It sounds like a lot. Each of us is producing between 6 and 17 tons of CO2 in a typical home with our electricity usage, okay? But look how much is in the atmosphere. So we're adding this right here. Let's say the worst case, 17 tons. That's where we are down at this end, and this is how much CO2 is in the atmosphere naturally. Okay. Yeah, go ahead. Yeah. Yeah, and that's what the whole set. I think we're probably going to run out of time, so let me go quickly. The atmosphere is absolutely huge, and that's one thing I think people don't get in their head, that we are capable, I guess, of. And I can't say we have zero effect, because zero is zero, but we're adding, let's say, 17 to billion, quadrillion to 2 quadrillion tons of CO2. We're adding 17 to that. Let's just take the worst case scenario. So you guys know about equilibrium. You make a change, and the system sort of tries to counteract that change. And so if we compare our biosphere to a system that's at equilibrium, The biosphere takes carbon dioxide and turns it into carbohydrates in cellulose, starch, and sugars. So if we treat this as an equilibrium system, and water, take the average amount of water in the atmosphere, which is about 2.5%, we have this equilibrium in petamoles. Okay, now this is a solid, so it's not in our equilibrium constant, but oxygen is. And so we can calculate the equilibrium constant for this steady state. And if we put in, let's say we took all 425 exajoules for the global consumption and converted that over to the worst source of fuel using coal, we would put in 1.21 petamoles of carbon. Now that's on the petamole scale. That's a huge amount of carbon. In fact, this is 5 times worse than the worst case scenario for the Intergovernmental Panel on Climate Change. So we took their worst case scenario, we went beyond it 5 times. Not 5%, but 5 times, 500%. And so this would be the change that we would introduce. It's a 1.9% increase. So this is our new initial. We do the equilibrium, minus x, plus x. And let's not assume that x is small. Let's leave the x in there and do this numerically. We didn't teach you how to do the numerical one in the freshman level because it requires a spreadsheet. You didn't know how to use spreadsheets, but we know how to use spreadsheets. So we'll leave the x's in there. And then this is the equilibrium piece. If 80%, so x is 0.8% of that change, so x would be 0.97, Q is 0.1331, it's not equal to K, so we're not back to equilibrium. If we made it 0.9%, 90% reacted, Q is 0.1333, it's still not equal to 0.1335, it's not the equilibrium constant again yet. We go to 94%, 95%, when we get to 95%, Q equals K, so we're back to equilibrium. So it will use up 95%. The biosphere will chew up 95% of what we put into it. Okay, and that's the worst case. That the whole world ran on coal and we got rid of everything else. Okay. Now that's putting that's putting in it would reduce that amount of CO2 from 1.21 to 0.06. That would be the result of what we put into the atmosphere each year. So the question is that something that the globe could handle? Okay, temperature difference. If the temperature goes up, it actually makes the situation better, not worse. So let's look at the carbon cycle. So burning these fossil fuels, we're taking it out of subterranean and we're blowing that carbon into the atmosphere. And so if we put up that much CO2, what are the other sources and sinks of CO2? Well, we have photosynthesis, right? And so photosynthesis can drag 60 to 150 petagrams of carbon out of the atmosphere each year. And we're only putting in 6. Max 15. Like if we did that 425, that would be 15 petagrams of carbon per year. And photosynthesis and respiration of bacteria are able to keep that in equilibrium. Forestation and deforestation, we hear a lot about that, but it's not so dramatic in terms of its contribution to the carbon cycle. In and out of the ocean is significant too. So these are balanced. So my point is, even if we ran the whole world on coal, we're not tipping the scale so much that the normal pumps in and out of the atmosphere are overwhelmed. So I like to think of it as the level of water in a bathtub, and you've got 3 pumps in there that are going in and out, and those pumps have a capacity. In forest, it's in the single digits, in the ones. In the critters, microbes, bacteria, plants, algae, those are running in the double to triple digits, and the ocean's running in double to triple digits. We're not stressing these pumps. So, last slide is the solar influence. So this is the energy balance. So that 100% of that light that's hitting the Earth, 25% is reflected from clouds in the atmosphere, 23 is absorbed by the atmosphere, and 46 is hitting the surface. Now, whatever hits the surface, if you got a nice shiny white parking lot, 6% of that is reflected, but it's also snow caps and mountains. The snow reflects most of that. 9% is emitted by the surface. Notice it's orange. So it's been absorbed and then emitted in the infrared. 9% is emitted. 37% of that infrared is absorbed by the atmosphere, and this is what keeps us from freezing at night. So this is the water and the CO2, the greenhouse gases that are keeping us warm at night, is that 37% that's absorbed. And then you add that 37 and the 23%, and then 60% is eventually emitted by the atmosphere out to space. So this piece right here is the greenhouse effect. And what we're doing is we're changing the absorptivity of the atmosphere a slight amount by putting out CO2. But water's driving most of that. So here's the atmospheric absorption spectrum. And you can see water vapor. So here's the total atmospheric spectrum. So this is opaque as the top. So these windows are closed. Closed right here, closed right here, closed right there, closed right here. So you see this is the total atmosphere. Look at water. You can see the atmosphere is mostly governed by water. Water is our most valuable greenhouse gas. CO2 has a few spots where it affects. And it's already saturated in 2 of those peaks. It's not saturated here, it's not saturated there. So adding a little bit of CO2 is going to affect these 4 windows. But you see that water is the main component of our greenhouse gas. So what do we believe? Well, listen to people who discuss the data, and I would say ignore people that call you an idiot, say it's too complicated to understand, that cite experts but don't really know how to talk about the science behind it. And so I would say go into all of this discussion with the confidence in your ability to figure out the numbers and understand the science behind it. Okay.